This is going to be a rather short video, so let's jump right into a recap. We can take the derivatives of trigonometric functions, exponential functions, as well as polynomial functions, but we still lack the ability to take the derivative of an inverse function. Well, the inverse of a function undoes what the function does. So if we had some function f that takes the number between 1 and 3 and maps it to the same numbers, f inverse, denoted with the power of minus 1, undoes the mapping. If f of 3 equals 1, according to the sketch of f, then f minus 1 of 1, notice that that's the output, equals 3, since it is like doing f in reverse. Likewise, f of 1 equals 2, so f inverse of 2 equals 1. And f of 2 equals 3, so f inverse of 3 equals 2. To write it out in function notation, this undoing can be summarized as f inverse of f of x equals x, and also f of f inverse of x equals x. You can think of the f and the f inverse as cancelling out, leaving x to remain. Using one of the inverse identities, we can write it out as a differentiable equation, replacing the inverse of f of x with g of x to make things simpler. The next thing to do is to simply just take the derivative using the chain rule. This gives g prime of x times f prime of g of x equals 1 after differentiating both sides. Now to find the derivative of the inverse, divide both sides by f prime of g of x, thus giving us that d by dx, f inverse of x, equals 1 over f prime of the original function of the inverse function. Let's look at the natural logarithm of x, the function that undoes raising Euler's number to the power of x. Writing out the derivatives of the original function, we get the exact same thing. So when we plug this into our formula, the derivative of the original function is still e to the x on the bottom, but the x is replaced with the natural logarithm of x. But wait, e to the ln of x is simply x by definition. So the derivative of the natural logarithm is 1 over x, the reciprocal function. How about arbitrary base logarithms? Well, if we set log base a of x equal to some number k, doesn't matter what k is though, we can then obtain x by raising a to the kth power to undo the logarithm. Then a to the k can become e to the k natural logarithm of a through some simple exponent rules previously explained. With this, taking the natural log of each side reveals that the natural logarithm of x equals k times the natural logarithm of a, and dividing each side by the natural logarithm of a yields that k equals ln of x over ln of a. Getting us back to the initial time we had k, then we could say that ln of x over ln of a equals the logarithm base a of x. Replacing this into the derivative makes this a very easy to compute derivative, giving us that the derivative of an arbitrary base log is 1 over x times the natural logarithm of that base. Here's an example. Say we have a function f of x equals x times ln of x. To solve this, we applied the product rule to the two indicated functions. The only thing different this time is that the derivative of ln of x is 1 over x. When the x's cancel out on the right, the final expression is the derivative of x ln of x is ln of x plus 1. Up next, we have the derivatives of inverse trig functions, and that about summarizes almost every common derivative. And until then, keep on learning.